Hello, so today we're going to make a spinning 3D cube, but in a very non-traditional way. So normally one would use something like OpenGL to render this, which is basically doing most of the work for you. We're going to do a very simple spinning cube, which is going to render in ASCII, in line with our principle of keeping everything very simple. So let's kind of start by creating a repository for this project, like this. So we're going to call it Simple Rust Projects, Simple Rust Cube, like this. And this is going to be a public project, and we'll put in a README and a git ignore for Rust, like this. And let's make it MIT license, for example. Do anything you like with it. Create a repository. Right, so now we've got a sort of shell of a repository. I'm going to copy the URL. Let's go over to a terminal. I'll make it a little bit bigger so you can see it better, or maybe not big. And we're going to clone the URL we just made, like that. So Simple Rust Cube. I must confess I have done this project before we started, so I've got a kit of parts to make this thing, but we'll do it bit by bit as we go along. Oops, how about Git? That's probably going to help. There we go. Right, so now we have Simple Rust Cube as an empty project, and if we open it with Visual Studio Code like this, and bring the window over, then we got ourselves a basic project. Now it's not yet a Rust project, so we're going to have to do a little bit of work with it. So back to our terminal here. We'll go cargo new simple Rust. In fact, I can do a cargo init in this directory, and that'll give me all the sort of bits necessary for a Rust executable. So cargo init, just the same as cargo new, except I don't have to specify the directory. And if I look in the source directory, I should have a ls source. I should have a main.rs, and if I cat my main, then you see it's just a hello world. Because it's main.rs, this means this is a executable we're building here. If it was lib.rs, it'll be a library. It's as simple as that. There's nothing particularly special we need to do this. And again, we're going to try and build this with as few as possible dependencies. So, expert programmers tend to use very few dependencies and make their projects very simple. So this is how you can tell the difference between an expert project and a beginner project. So let's have a look back in the editor here. So we now got a main.rs like that with hello world. We don't want to say hello world. We're going to draw ourselves a cube. So what does our cube look like? I've got a convenient piece of ASCII art which will kind of illustrate what it is we're trying to do here. So here we're using / exclamation mark, which are module level, or what's called an inner doc comment, which documents the thing it's in this case the module. So our cube is a 3D object, has 8 vertices and 6 faces. That's a kind of definition of a cube. Of course, they're all perpendicular to each other, which also makes it a definition of a cube. So here we have some vertices. We're going to define these vertices in a little while, and we're going to try and render this something a bit like this on the screen. So we'll do a thing called backface culling, which makes it a little more readable, and we'll also do it in perspective, which involves doing a divide. After all, things which are further away appear to be smaller. So that's the sort of basics of our cube. We also need a little bit of algebra. So Again, I'm not going to use. There are some quite decent algebra libraries out there for doing 3D algebra, but again, it's not particularly necessary in this case. So we're going to build it all from scratch and show you how it all works. We're not just picking things up and putting them together. We're not ordering a pizza. We're making one ourselves. So the matrix basically is an array of 4 arrays of 4 numbers. This is a 4x4 matrix. Each of our inner arrays, these things here, contains 4 floating point numbers, which represents a column of our matrix. So we tend to think of it's a convention in computer graphics to use columns, column-based matrices. So each of the vectors here represents a column. When we multiply the matrix by a vector, by post multiplying by the vector, then we essentially scale each of these vectors by elements in the vector we're multiplying by. And our vector is also relatively simple. It's just an array of four numbers. That could be one of the columns of my matrix, for example. So in 3D algebra, we kind of represent the corners of this cube, for instance, as vectors. We've got one more element, which is usually a 1 in the case of vertices. So we put a 1 in the last digit of our vertex. But we've got 8 vertices to define, which is a relatively small number. So let's define those vertices now. And again, here's one I prepared earlier. So this has been built basically by kind of starting with the first row and then just flipping some of the minuses. So in this one, the minus gets flipped to a plus. In this one, more minuses get flipped to pluses, and so on. So we end up with all 8. So basically a binary truth table of the vertices. So and this last column is always 1. So with positions in computer graphics, then the last column is always 1. The last row is always 1. These are actually columns, and if it's 0, that means we're representing a distance, a direction, rather than a position. So positions have 1s and directions have 0s. So that's just the positions. We also need to represent the faces of the cube. So what this little array is an array of indices for the faces of my cube, and each face has 4 of these indices. So these are just which index represents which face of my cube. So if we look at 1573, for instance, then 1573 gives us the face of our cube. The order of these is quite important. So we're going clockwise in this particular case. So we go 1573. On the back one, we're going to do like 2640. So when you look at it from the other side, then the order is backwards. But at every face, if you look at it, then it's always going clockwise. And I'll show you why this is important later on. And so we need a little bit of matrix algebra. So I'm not going to define an algebra by overloading operators for my vectors and things. It's rather unnecessary. So I'm just going to provide a function which does matrix times vector. So we go to a matrix, we go to a vector, and we're going to multiply the matrix by the vector. How does this work? Well, we kind of we use destructuring to unpack the columns of my vector into mx, my, mz, and so on. And I unpack the rows of my vector into x, y, z, and w. W is always 1 in this case. It doesn't really matter. It's not always going to be the case, but that's how it works. So you could save a little bit of time by not multiplying by w, for instance, just adding in the mw. But we're doing this in a fairly general way. It doesn't really make a lot of difference at the end of the day. It is not high performance software. So that's our sort of basic cube. We can do this little trick to help us rotate the cube, because we can make a matrix which represents a rotation of the cube. So if you kind of imagine the matrix as a bunch of axes which are kind of rotating and a position for the axis coordinates, then the columns of my matrix represent the axes of my rotation matrix, and I can move. That means I can move and rotate the cube around by pointing the axes in a different direction, and that's a fairly simple algebra. So what are we going to do to render this? So we're going to need a screen. So let's kind of start with our definition of our screen. So in this case, we're going to render it in ASCII. So our screen is actually quite low resolution in this case, 40 by 80, which is not terribly high resolution. But there's no reason why you couldn't do much higher resolutions if you wanted to. So there are ways of rendering 3D graphics using a CPU rather than a GPU, which are actually quite fast. But they're a bit more tricky, which is one of the reasons why GPUs are so popular. But CPUs are actually quite good, and with a decent CPU, you can outperform a GPU in particular circumstances. And I'm also going to define an offset and a scale, and this basically lets me kind of center my cube in the center of my screen, which in this case is going to be some ASCII characters. So that's the basics of this. We've made kind of a screen definition. So we've got the width and the height of our screen. We've got offsets and scales defining the transformation onto my screen. So this should kind of take something which is like plus or minus 1 and kind of map it onto my screen in a fairly simple way. Right. So next thing to do is to write a rendering loop. And because this is going to be an animated cube, so if I do for so call it frame number in naught dot dot, now naught dot dot is an open-ended range, so it will just carry on forever, generating frame numbers for me. So frame numbers in 3D graphics kind of represent the time essentially that you're rendering at, and so typically we tend to kind of render at a fixed interval, and so the frame number will be representing our time. So we also need something to render into. So let's make a frame buffer. This is our frame buffer. So this is just a bunch of bytes, which is like width by height. This is a matrix of bytes, and these bytes are going to be our ASCII characters, which represent our ASCII screen, which we're going to render. So most games you can make using ASCII rendering, and it's very, very simple. So if if you're working over a very limited connection, then it's all very easy. But most games are very easily made as ASCII art. So the next thing we want to do is to make a transformation for our cube, because we're rotating our cube, and so the first thing I need to do is make a time, which represents the time. So in this case, I'm taking my frame number and I'm multiplying it by a small number. So this gives me a relatively slowly incrementing time. And the next thing also I'm going to do is define a cosine and a sine. So if you imagine the cosine I'm defining here, if you plot these on a graph, essentially we'll have a clock. The cosine is the x direction of the clock, and this sine is the y direction, the y direction of the clock. So the clock handle slowly spin round, and the clock will rotate. But what we're going to do here is we're going to spin my cube. So instead of making a clock, we want to kind of make a matrix, and this is a matrix which will spin my cube. So remember, each of these things is a column. In In the case of directions, then the columns, so this is an axis, so it has a direction, so the last column is a 0. So that's the x, y, and z directions of my matrix. This last one has a position. This represents the origin of my matrix. So this matrix is going to spin my cube around a vertical axis. We could do more sophisticated things. We could, for instance, tumble my cube by successively multiplying it by a small angle, for instance, in 2 different axes, and that will cause it to tumble. But in this case, I'm just going to do a simple transformation, which is rotating the cube about a vertical axis. So that's defined a matrix, and that's going to be changing with time. So as my frame number moves forwards, then the matrix we're using to render my cube is going to change, and the axes are going to move around, and with the axes, the cube itself will move around as well. So what I'm going to do next is to use this matrix to transform my my coordinates of my matrix into screen positions, which has a few components to it. So this is a loop which will build me an array of screen positions. In this case, they're just 2-dimensional coordinates, so there's 8 screen positions for my corresponding to my 8 vertices here. And what this will do is kind of give me screen positions for each of the world position or model position vertices in my vector. So the first thing I do in the loop is I'm going to loop over all the vertices. So I'm just do for vector and screen position as a mutable, and I'm going to write to this S, and I'm going to read from V. So first thing I do is I make a world position for my vertex of my cube. So in this case, I'm going to use the matrix times vector function to do that multiplication, and this will transform my cube into world space. Like, this means I'll be able to move the cube backwards and forwards, up and down. I could bounce it around in the world, or spin it about, do physics on it, for example, or all very straightforward stuff once you know how. I also calculate 1 over the z coordinates. This is a very simple projection where I'm just dividing by the z coordinate. In sort of OpenGL, for instance, we do a little more complex stuff because we also generate a scaled z value. But in this case, I don't have a z buffer. I'm just going to divide by z to make things smaller in the distance. So I'm going to take the world position, and I'm going to take its. In this case, the world position has a 0, which is the inside of my vector. So that's the dot 0 in my vector. So in Rust, when we have a tuple struct like this, then the dot 0 is the thing in the parentheses there. So we take the world pos dot 0, we take its 0th element, which is its x coordinate, we multiply it by reciprocal z. But why don't we just divide by world pos 2? This is because dividing is very expensive, and we only want to do it once if we can possibly avoid it. So in high performance code, we only divide once typically, and we also multiply by my screen scale, which we've defined up here, and we add our offset x. So this kind of centers it in the middle of my screen, which is the sort of 80 by 40 screen I've defined in ASCII to define my screen. I also do that with the y coordinate, and that will center it in my screen. And now I take the x coordinate and the y coordinate into a temporary array, and then I assign that to my screen pos, just like that. So it's very, very, very simple to do matrix algebra without using a library in Rust. So having got our points in screen space, I could, for instance, just plot those points in screen space, and we could see how it all works, for instance. And but what I'll do is I'll probably go through to the end and kind of show you all the steps, and I could come back again later on and show you some of the detail. let's draw lines to represent our faces. So I'm going to start with a fairly simple loop like this. So I'm going to go take the faces from my cube, which represent the indexes, into my vertices to draw my cube. I'm going to eventually draw some lines for these faces. So let's do that right now. And I've got this function called draw line. I'll show you how that works in a wee while. So what draw line is going to do is going to draw some sort of dots or pluses or slashes or whatever to show you what my line looks like. I'm going to use the screen positions at the start and end of my line. I need one extra position, so I'm going to take the last vertex in my face and call that end, and the start so the first one will actually draw from the end of the face to the first coordinate of the face. But we're going to draw 4 lines in total for my face, and then at the end I set end to start. So we always end up with start end, start end, start end. So in the case of my first one, for instance, will be sort of 3 to 1, and then 1 to 5, 5 to 7, and 7 to 3, and cyclically around the face of the cube. So draw line is a function I'm going to define in a minute to do that drawing. So let's leave that out for the moment. What the next thing to do really is just to render my screen, and rendering this is very easy. So let's just I'm not going to draw it. There's going to be a blank screen to start with, but if I put this bit of code in, then what I can do is I can iterate over my screen, which I've been writing to here, and I'm going to convert each of the lines of my frame into a string from UTF-8. Converts from UTF-8 characters to the string. I know I can unwrap here because it's all just ASCII. There's no characters greater than 128 in the character set, so this will never fail. So I can generate my row like this, and I can print the row. Just printing the row is how we render this thing. So before I draw the line, let's just draw the vertices maybe. So for instance, here for instance, I could just draw the vertices as they come into my frame buffer. So if I just go screen, and I do like y coordinate, x coordinate, because that's the way C arrays work, and we're using C arrays here. And I just set, if I just draw a dot, for instance, at that place, so it's called a screen buffer, I think. Yes, frame. It's called frame. There we go. Frame. So we're just going to set some things there, and I also need to cast these into usize. So I'm just doing a C-style cast here, full of peril, but I'm going to set a point in the buffer. So far we've got relatively little code. We've got like 100 lines of code here, and Rust analyzers showing a couple of errors. Let's fix those. I cannot find Y in this script, so it's actually screen Y. I can get away with this because screen X and screen Y are integers and are floating point numbers, and they're copies, so I don't need to worry about the fact I've moved them into this array. And if I put a B in here, then that's fix another problem. And of course, it's complaining that I'm not using end or start here. But so I'm just going to do a very simple render and see if it works. No idea if it's going to work. Let's give it a try. Oops. Right, so that's a bit boring because everything's going a bit too fast. Oh, let's put a little delay and That'll slow things down a bit. So I'm just going to sleep the thread. Not normally a good thing to do, sleeping threads. If you know a little bit about async, then there are other ways of sleeping a task other than sleeping a thread. But in this case, we're going to sleep the whole thread. Call us barbarians if you like. Right. So here we have it. We have a sort of very basic rotating cube. At the moment, you can just see the sort of vertices spinning around. We can't see very much because it's gone off the top of my terminal, but you can kind of see the bottom of the cube there rotating around. As you can see, it as the points in the distance get smaller, so that distance gets smaller as we go further away, whereas it gets bigger as we get closer here. We can fiddle around with the matrix to reposition the cube and to change how our perspective works, for example. But at the moment, this is kind of imagine this as the bottom of the cube, which is spinning around. So another thing we want to do really is to clear this, or at least clear the screen, or at least reset the cursor. So if you see some of my previous ones, then we're using ANSI escape sequences. So 1B is escape, open square bracket, screen height, which is the height of my screen, and A moves my cursor back up n lines, in this case the screen height lines. So let's try that. So it's instead of it scrolling, which you couldn't really see, then it should move the cursor up to the top. So it's a bit better behaved now. You can kind of see the top of the cube if I spin the window up to the top like that. So that's the sort of basic sort of 3D render stuff. Sort of back many moons ago, this was the only option we had to draw 3D graphics on teleprinters, for example. But these days we have sort of flashy frame buffers and screens, and memories are millions of times bigger than they were back in the old days. But there were a lot of games which just ran on teletypes, and quite a few of which rendered 3D scenes on teletypes. So unless you happened to be rich, you couldn't buy a graphics display. So let's get on and kind of draw my line. So I'm going to comment out that this line which draws the thing, and we're going to draw a line in our frame buffer. So we need to define this function called draw line. So here's one I prepared earlier, just to drop it in on you like this. So this is a function called draw line. So draw line takes 3 parameters, one which is the frame buffer that we're drawing into, and 2 which are the start and end in screen coordinates of my line. In this case, the screen coordinate is very basic. It's just ASCII, and these numbers are 32-bit floating point numbers. In the game world, we use 32-bit numbers rather than 64 because they're a lot faster. Typically, so if you're using SIMD arithmetic, then there's big advantages to using smaller number sizes. So 16-bit floating point numbers are also possible. First thing we do is you kind of put our deconstruct our start and end into sort of x0, y0, x1, y1 for the end. This is our delta, our direction of our line. So the end minus the start, in the y's. So this will be, if we've got a vertical line, this will be 0. If we've got a horizontal line, this will be 0. Otherwise, these will be non-zero. So we've got 2 different types of line we want to draw, which are kind of quite different. When we're drawing vertical lines, we only want to draw 1 character per line, and when we draw near horizontal lines, then we want to draw only 1 character per column. So we split this up into two drawing loops. The first this abs tests whether our difference in our y is greater than our difference in x. So if this is a largely vertical line, then it'll run this piece of code, and if it's a largely horizontal line, it will run this piece of code. So we need to kind of look at our minimum y value. So we're going to draw from the minimum to the maximum in this particular case. We're going to draw from actually the top to the bottom, because our y coordinate is sort of 0 downwards in this particular coordinate system. And I'm going to kind of make min-max y's in floating point and min-max y's in integer. This is because I need to draw a specific number of lines in my specific number of integer cells in my loop. Generally, we don't write loops using floating point numbers. That's a bad idea. Instead, we use integer coordinates. Again, what I'm doing is I'm pre-dividing x by y in this particular case. Give us a dx by dy, and because I don't want to do a divide inside the loop here. Multipliers are much more efficient. We don't want to do any divides here. So in this case, what I do is I subtract y0, which is the beginning of my line, multiply by dx dy, and that gives me the x offset along the line, and then add in x0, which is the start point of my line. So I subtract out I turn the y coordinate back into a floating number, subtract off the y, multiply by dx dy, and that gives me the x coordinate of my, and add in x0, that gives me the x coordinate of my point, and then I just set. In this case, I'm doing a vertical bar to represent vertical lines, and I'm doing a horizontal bar. I'm doing a dash to represent horizontal lines. Of course, we could do this much more cleverly with UTF, using Unicode characters, for example. But this is just a toy to show you how to do 3D graphics without any crutches. So that's going to draw my vertical lines. The horizontal lines are similar. I need to get the left hand side by doing the minima of the minimum max of the lines. I can then construct my loop. So this gives me I min and ix min and ix max, which are the columns of the line I'm rendering. And then for each of those columns, I can turn it back into floating point, calculate the y position, and plot the x and y as a dash in this particular case. So I know this works because I've done it earlier. And if we look in problems again, then we don't have any particular problems. So if we had an error somewhere in there, then a problem would pop up like this. We can click on that and say, I have an exclamation mark. Let's fix that. So very, very easy to fix problems in Rust. Notice I'm not using vex at all. Not using dynamic allocation anywhere in this. This is very nearly a no-stud program, which doesn't use any memory allocation. This is quite deliberate. And so let's run the program and see if it actually works. Behold, it does. So I must confess it took me a while to get this going. Now this is a wireframe cube which is spinning in 3D, but it's kind of hard to tell which is the front and which is the back of the cube. So in 3D graphics we kind of like to see what's the front and what's the back. So normally we have a Z buffer or Z buffer for our American cousins, and we draw all the pixels in a face, for example, and we also record the depth. And if we draw the back before the front, then we overwrite the back with the front. If we draw the front before the back, then we overwrite we keep the front and don't write the back. So we use the Z buffer to decide which bits are in front of which bits. But in wireframe we don't have that luxury, so we use a little trick. Remember I was very careful to design the cube with a clockwise coordinate system. So what we want to do is to kind of look at the direction of the join of our lines. So if we're drawing lines like this, then if we're drawing clockwise lines, we want to draw them. If we're drawing anti-clockwise lines, then we're not drawing them. So so we can kind of look at our face and do a thing called a back face cull. So this is a little function called cull, and I'm going to put it in here. So what cull does is takes 3 points, point 0, point 1, and point 2. It does essentially a cross product on these a 2D cross product on these points, essentially measuring the area of the triangle that they subtend. And then if the area of the triangle is positive, then this thing will come out true. If the area of the triangle is negative, then this thing will come out false. So we can use cull to tell us whether the faces we're drawing are clockwise or anti-clockwise. If we kind of look at our drawing here, then the back one would have been drawn anti-clockwise like that, and the front one would have been drawn clockwise like this. So by looking at these corners, we can work out whether it's pointing forwards and backwards. In the case of a cube, it's very easy because we've got near 90-degree angles between our faces. We have to do it on one vertex of our face. We can cull the entire face. So let's have a look at that. So what we're going to do is we're going to cull the entire face by looking at one corner of the face. Really, what we should do is measure the area of the whole thing, because we're drawing quads. But I'm going to cheat a little bit. So this call to cull will basically stop it from drawing back faces of our cube. So if you ever play games like Elite, then this is the way they avoided drawing the back faces of the spaceship. So Elite is a very similar system to this. You could probably write Elite in a few lines of Rust if you really had to. So this is going to do a back face cull. So I'm taking taking 3 of my points of my face, and they're taking their screen positions and doing a little cross product on them to measure the direction that they're turning, and this hopefully should cull the back faces of my cube. So let's run that, and we get something a little better. It's not brilliant. It's not fantastic, but if I shrink it down a bit, then we can probably see a few more lines. So there we go. We got a few random lines because I grew the screen, but as you can see, it's only drawing the front of the cube. So that's a sort of very basic rotating cube. So exercise for the user is draw some textures on that cube. Make Wolfenstein out of this. Not too difficult to do that kind of stuff once you've got this sort of basic stuff in play. Top tip: don't make it complicated, because 3D graphics actually is very, very simple. You just need to know the basics of it. So if you get the chance, read a very good book called Game Engine Architecture by Jason Gregory, and a very nice chap as well. And he's written a very good book which explains this kind of stuff in more detail. So that's the conclusion of it. I'm going to post this on GitHub. So in fact, the sort of last thing to do is to do that. So if we look at the files here, if I add them like this, I can now say spinning cube done, and exclamation mark, and synchronize changes like that. Go bumpity bumpity bump, and if we go to GitHub and refresh the page, then we should have a simple Rust cube. There we go. Well, I hope you enjoyed that. I'll try and do some more videos of this kind. So please give me some feedback and some likes and such like. It's been very interesting doing these things. I'm a complete newbie to YouTube, I'm afraid, so the video production quality is absolute rubbish. But thank you very much for watching this video all the way through, and a big pat on the back, and thank you very much.